Okay, I would like to thank the organizers for the invitation to come and celebrate.
Should I introduce you?
What's that?
Should I introduce you? Yeah, that's
Okay.
Professor Warren Pickett, who will tell us about lanthanum, nickel, gallium-2, and fragile magnetic superconductors.
All right, and the title is up there. Yeah. So we're celebrating Allan's career, basically, accomplishments. When I got the invitation, I thought, sure, I wouldn't miss it. Wouldn't miss coming. And an hour later, after I think I had accepted the invitation, I got to thinking, I don't live in Flatland. Yeah. I read the book when I was 12 or 14 and loved it, but I don't live in Flatland. I've done a lot of work on oxide interfaces, but that's not current. So I had conversation with Fan a little bit. He said, if you talk about current science, you'll be in pretty good shape. So that's what I'm going to do. My talk is not going to be what the organizers might have expected me to talk about. I won't spend much time on standard model physics, but the little bit I show is interesting, giving contributions, complications from quantum mechanics, basically. So John has sort of ruined this slide for me, because when I think it was Sammy asked if there was anyone that collaborated with Allan during his NRC days, I was slow to raise up my hand. And yesterday, I could have won a bet if I'd said I was the first one in the audience to collaborate with Allan. But since John showed up, I can no longer claim that. Let's see if we can get to stay up here. The title of this 1980 paper is a little bit obscure. So if we get the title. 1979, I was a postdoc at Northwestern, spending 2 days a week at Argonne, working with Dale Coley and using their computers. And for some time, a few weeks, whatever, Allan came down from Canada. And what we did was to, maybe I'm touching this too much, take Dale's fully relativistic augmented plane wave code, which is basically the exact solution to a given crystal potential problem, cone sham type of solution, but it's very slow. And the good computers at Argonne were getting busy. So what we did was to produce a scalar relativistic APW, which is everything relativistic except spin orbit coupling, and then included spin orbit coupling. All right. So this paper just should tell you everything you want to know about spin orbit coupling, right? That's supposed to be humorous. All right. Let me talk about the first part of my title, lanthanum, nickel, gallium-2, a putative triplet superconductor. And one of my colleagues put this putative in the title because of some of what I will talk about here. So I'll call this LNG2. All right. And I don't know what's happening here. In 1982, a group in the former Soviet Union, which included Yuri Green, who's become very well known as a synthesis and characterization person, they made lanthanum, nickel, gallium-2 and identified a space group, a CMMM, from powder diffraction. And this is non-centrosymmetric. So it was interesting because of that. In 2021, my colleague Valentin Tofur decided to grow single crystals of LNG2, and extra spots were seen, and it turns out it's CMCM, which is centrosymmetric, but it's non-symmorphic. I'll say a little bit about that. All right, what's happening? Okay, on the right is we have to deal with my tremor here with this thing. On the right, okay, the difference in the structure is mainly the position where the gallium atoms are, but it makes a difference. Okay. So here are the band structures, the bottom CMMM and the top. And what you see, it's actually not simplified throughout, but on these last few panels here, you can see that there are fewer bands in the CMCM band structure than in the CMMM band structure. And that's because something that's well known, because states in non-symmetric crystals on certain planes can stick together. So all of these bands up here are, and now the pointer's not working, but the bands at the top are on what I call a wall of degeneracies, which my co-authors wouldn't let me put in publication. And to look at the band structure in that region and include spin-orbit coupling, what you see in this, everywhere bands crossed or were degenerate, the degeneracy is lifted. There's anti-crossings, except along this very last panel, T to Z. Okay, that's special. Those bands aren't touched by spin-orbit coupling. And here is what's happening. The Fermi surface of LNG2 is shown there. And on this wall right here, which is emphasized in the figures, if a Fermi surface comes through there, then it will be two Fermi surfaces touching. So they're fourfold, two spin, two orbital degenerate. And Fermi surfaces 2 and 3 stick together on the lines of degeneracy, and bands 4 and 5 stick together on the loop there. And yeah, okay. So this is just indicating that another colleague, Avishik, has done very extensive RPES work on this and verified the band structure and even the Dirac points pretty convincingly. Okay, a little bit of history. I can imagine in 1936 that Wigner pulled his new student, Conyers Herring, into his office and said that Wilkert, Smoluchowski, and I did all the group theory and so forth for energy bands and crystals, and we know all about the degeneracies for different symmetries. What I want you to do is to go out and look for accidental degeneracies. And Herring did that, published the paper in 1937. Also, I managed to get, for 6 months, his thesis from Princeton and go through that. 5 copies were made, apparently, 3 sent to universities in Europe, 1 kept at Princeton, I suppose 1 in the family. His synopsis was, accidental degeneracy should be common, lines of degeneracy should not be uncommon. Okay, here, another Herring, R.R. Herring, a Canadian theorist, in 1958 published this paper, very nice type binding representation of rhombohedral graphite. And what he identified was, in addition to describing the electronic structure and so forth, was that there are these loops of degeneracies, nodal loops in rhombohedral graphite, which came out of his type binding model. And you know, the loop, what it shows here is a third of the Brillouin zone, and it will repeat through the next Brillouin zones. Okay, so that's the first instance I know of someone finding nodal loops in a real crystal. Then in 2007, Phil Allan, who was my thesis advisor, looked at the band structure of aluminums doing calculations, and he discovered that there's a nodal loop from this point to this point through the Brion zone, and also from this point to that point through the Brion zone. He said, no big deal, sort of expected something like that. What he was interested in is what happens to the geometric phase when spin-orbit interactions lift band degeneracies. These nodal loops have a topological phase of pi, and what he wanted to know is how spin orbit affects pi. And what he found was that it lifts the degeneracy, and the integral over the contour is no longer pi, depends on the orientation and size of the contour as usual. So then it's no longer topological. And he put a very elegant, mathematically elegant paper on the archive, and said, I thank the students in my solid state physics course who were subjected to preliminary versions of this work. But he didn't find it to be really ready for publication. And this is 2, 3, 4 years before nodal loops were discovered and started to sort of pollute the literature with all the nodal. I helped with some of that. All right. So that's not what I want to talk about. Here's what I want to talk about. LNG2 was found from powder samples in 2012 to show this signal from muon spin relaxation below TC, which indicates a magnetic moment is, a magnetic field is affecting the spin of the polarized muon that's sent in, and it's a triplet superconductor. It's a magnetic field accompanies the breaking of muon symmetry. And then the theorists got busy with constructing what they could do for the most likely order parameter, which has 3 components. So let's get to the fragile aspect here. I tend to think of triplet superconducting, parallel spin pairing up and down, parallel spin pairing down, as really being really something different. So here is a compilation of what was known of these fragile magnetic superconductors as of 2021 by experts in the field. So these are mostly experimentalists co-authoring this, but they collaborate and work a lot with experimentalists as well. There are 20 of these. The top 4 I'm not going to consider because those are correlated electron materials, but the bottom 16 are just sort of ordinary Fermi liquids in the metallic state, and when they become superconducting below 2 Kelvin, this signal is seen. And you can see that the symmetries vary a lot, so it's not an aspect of symmetry. And also, I think all of these, well, maybe not the third one, others were identified first by MuSR and then collaborated to some degree, corroborated by Kerr effect measurements. Now, the second column of numbers provides the inferred magnetic internal field, the spontaneous field. And those are in millitesla. And so actually the numbers are 1 Gauss or less. Really small fields. If you think about the energy related to 1 Gauss fields, really small energies. And many of these papers mention that this detection of fields of this strength is right on the edge of detection, right near the edge of detection. And the same for the Kerr rotation. There, the rotation where they see it is something like 1/10 of a microradian. I can't even imagine measuring that. But anyway, that's near the edge of their detection. All right. So zero field muon spin relaxation is what is identifying these signals. And quickly, polarized positive muons are injected into the solid. They come to rest in an interstitial position away from positive ion cores, and usually, almost always in zero symmetry points somewhere in the heart rate potential. And the coupled sample already breaks time reversal symmetry locally. And that's as locally to the region of the muon. But on the other hand, the measurement is taken exactly from the position of the muon. So when the muon decays, here's the standard model stuff. You need to think about the antiparticles here. The mu plus decays with a half-life of 2.2 microseconds into an antineutrino and a W, and the W decays very quickly into a neutrino and a positron, which is what is detected. Okay, and this is the most common decay. It's not the only decay, but it's the most common one, and I think it's really the only one that's included in the analysis. Now here, this is what quantum mechanics limits what we can get at. Okay, the muon is polarized to the right in this picture, and the positron comes out with a variable energy, random energy between 25 capital MeV and 50 capital MeV. That's a quarter of the muon's rest mass energy, or a half. And at the low end, the emission of the positron is isotropic. At the top end, it's the solid red line, and it's what is called, well, what has to be taken into account is an average over the energies, which I have not seen done. But what you can see is, although this is called predominantly forward direction emission of positrons, it's hiding a lot of information. It's nothing like a classical arrow this way, rotating this way. When this starts to depolarize, this whole thing rotates. And you can see that the signal is, there's still, of course, backward emitted positrons. And what is done is have collectors over here and collectors over here, forward and backward, and project all those onto two sets, forward and backward, and look at the asymmetry. And if the asymmetry changes, then it becomes superconducting. Okay, this is just examples of the data. Here is lanthanum nickel carbon 2, which is also identified as one of these, and two different sets of data. They're green and blue, and also white. Maybe it's three. Indicate that it's sample dependent, and the practitioners admit there's sample dependence, and in particular, the muon might prefer to lie near a defect, a grain boundary, something like that, and they use what are sometimes called microcrystals. And over here on the right, this is just an instance of another compound, and a signal is seen when they analyze the data in the Gaussian channel, don't ask, but it's not seen when it's identified in the Lorentzian channel. And if it shows up in one or the other, it's identified as time reversal symmetry breaking. Okay. So a magnetic moment in a superconductor produces a supercurrent, a magnetic field in general. We're interested in a moment, but Bunsen's main contribution was getting this equation that the supercurrent is proportional to the vector potential. The electrons don't react to the magnetic field, but they react to the supercurrent in a superconductor with a constant penetration depth, lambda. Well, Ginsburg and Landau theory gives something different. It gives something very much the same. This is interpreted as the density of Cooper pairs, which is half the density of superconducting electrons. So this term looks a lot like this, except it's R dependent in this varying magnetic field. And it's also got this gradient of the phase of the order parameter, which is often called the stiffness, superconducting stiffness. Then in 1993, Chandrasekhar and Einzel took the BCS wave function and worked out this relation that the supercurrent is nothing to do with the density of electrons, superconducting electrons. It has to do with the density of states at the Fermi level and the Fermi velocity squared. And then there's a supercurrent, which is temperature independent and has this magnitude at t equals 0. This quasi-particle term is 0, but it grows as you raise the temperature toward Tc, and at Tc exactly cancels out the supercurrent. It's a different interpretation than one normally has for the supercurrent in a superconductor. As far as I know, these two methods haven't been used in analysis of the experiment. And still, certainly all the language is in terms of the London theory, which I think is just highly misleading. All right, here is an example. This is LNG2, Valentin's analysis of this, and for HC2, HC clean limit, dirty limit. This sample was clean limit, and HC1 and the thermodynamic critical field HC. These numbers are all representative of what we see in singlet superconductors with low TC that are not identified as time reversal symmetry breaking. And in particular, the coherence length C and the penetration depth lambda. And this analysis comes mostly from Ginsburg-Landau theory and assumes singlet superconductivity. And in fact, it's pretty well understood that triplet superconductivity would behave very differently. Upper critical field might be incredibly larger. All you have to do is to just tip a few down paired electrons to up paired electrons without breaking any pairs. Okay, so all these properties are consistent with a singlet superconductor. Now, when you have a supercurrent, which comes from some expression or is calculated from some expression, then you can use Maxwell's equation to calculate the magnetic field that results from that supercurrent. And what we're interested in is the magnetic field at the site of the muon, and there's the expression for it. And it's a nice simple expression. Unfortunately, the vector potential goes as 1 over r squared. This term goes as 1 over r squared. Here, there's an r squared in the numerator, but this integral as written is badly divergent, infrared divergent. That means there's physics close to the muon that needs to be taken into account. Now, just to point out here, this is from a DFT calculation of a position of a muon in this crystal. And this is the positional uncertainty that it's known to be important in many cases for protons. Proton is like a positron, except it's 9 times heavier. And you can see it's a fairly large uncertainty, positional uncertainty. And that, I think, should be taken into account finally in analysis of these experiments. They are using density functional theory a lot to identify these regions and also to identify the most probable stopping point for the muon, the lowest energy position of the Hartree potential. So this magnetic field, which we can't calculate yet, I think it's going to be complex, but it turns on at TC and it gives a field at the muon site. So I think that this always happens whenever you put the muon into a superconductor. And in some of them, the field that produces at the muon site is just below the level of detection. And for some of them, it's above the level of detection. All right. One example of, I don't know what to call it, 1998, strontium ruthenate, which has been studied a lot, but it's a Fermi liquid, strongly anisotropic tetragonal Fermi liquid above superconducting transition temperature of 1.5 Kelvin. And in 1998, it was one of the early ones to be identified as time reversal symmetry breaking. Now, Maeno was one of the co-authors of that paper. He's also lead co-author on another paper, 2024, which says, in particular, it was thought that the spin triplet chiral P-wave superconducting state, which breaks time reversal symmetry, was a prominent possibility. In 2019, however, a new development overturned the past experimental results and spin singlet-like behavior became conclusive. I think these are mainly NMR experiments, but maybe a couple of others. I haven't read this 45-page paper thoroughly. Okay, so just to conclude, I don't need to go through all these points, but sample dependence is bothersome. And the muon-induced local magnetic field below TC is something that really needs attention. And other areas also, there are other complications that I've run into in trying to understand this for the last 2+ years. And high quality single crystals will probably be important to help sort out this. So with that, I will conclude and be happy to take questions.
Okay, yeah, so Eva, if you could come up and get set up and we can take questions while she's doing that.
You are, and thank you for the history. Strontium ruthenate was of great interest to people who are interested in topological quantum computation and Majorana mode and so on. So I did work on it like 20 years ago, but the consensus.
So what was the first words of your sentence? What?
It was very popular among people who are interested in topological superconductivity,
Okay.
because it is a potential platform for doing topological quantum computing. Because if it's a spin triplet topological superconductor, you'll have Majorana zero mode.
Yeah.
But in that community, at least, which is a bit distinct from pure superconducting band structure community you're talking about, the consensus now seems to be, except for maybe one or two people, one person in Illinois, one person in Penn State, is that it's a singlet superconductor. I'm not sure to what extent it's accepted, but in the topological superconductivity community, it seems that it's a story that has ended. It's singlet.
It is singlet. What does it mean now here?
It means these NMR measurements basically are the decisive signatures.
Of mini material.
Yeah.
Okay. So I didn't say explicitly, but these Dirac points would remain even in the presence of spin arc coupling. And they're right at the Fermi level. But unfortunately, there are these huge 5 Fermi surfaces with densities of states at the Fermi level also. So we haven't figured out yet a way to make use of them or even detect them, except from ARPADS, which shows the right band structure.
Are there other questions? Okay, if not, let's thank the speaker again.